Hi everybody. So we have been talking about types of chemical reactions in class, and what we're going to learn about tomorrow is how to predict products for the different types of chemical reactions. So before we get there, this is just some video notes to help you fill out in your Unit 5 notes packet. I'm on page 7 of your Unit 5 notes packet. We are going to just bundle all the information we know about the different types of reactions, so that way tomorrow when we learn how to predict the products for them, we can just spend a lot of time practicing since you'll have the basics down. So the first type of reaction we're going to start with is synthesis or combination. Can go by either name. So if we're thinking about a synthesis or a combination reaction, it literally tells you what the reaction is in the name. It's combining all of your elements together to produce a compound at the end. So for our description, you can have two or more elements that combine to make one product. So the general reaction format box, I'm just going to use letters like ABC to help you figure out what they actually look like. But if we have singular elements here, that also includes diatomics. You could have something like A plus B2 plus C. These are all singular elements that combine together to produce maybe compound A, B, C. And then to balance this, you would just, at the end, put a 2 there, a 2 there, and a 2 there. So this is a general reaction format. You have a bunch of stuff on the reactant side combining together to form one product. For our purposes, we are going to see, for anything that I have you predict products for, we're going to predict products only for the synthesis of ionic compound formulas. So our reactants that we're going to see are a metal and a nonmetal. Metal and a nonmetal. So anytime I ask you to predict products for a synthesis reaction, you're predicting the formation of an ionic compound. This is not the only type of synthesis reactions that exist, but this is the only ones that we're going to predict products for. So if I ask you to identify a reaction and you note that it's synthesis, you would know that there's a bunch of reactants coming together to form one product, but the only ones you'll have to predict products for are ionics. So to predict the products, the steps to do this would be make an ionic compound. Ionic compounds come from charged ions, which means that you need to be able to pick out the charges on your ions, whether they're just elements that are forming ions. You can do that from the charge trend on the periodic table. Or if you have polyatomic ions, you need to know those charges that they'll form. So to make an ionic compound, you use that crisscross method. So here the charge from the cation will come down to become the subscript for the anion. Charge from the anion comes down to become the subscript for the cation. So you determine ion charges and crisscross. We'll get some practice with these in class tomorrow. So I'm going to leave the example section blank. You can fill in any example of a synthesis reaction that you come across in any of our assignments to give yourself a reminder of what this would actually look like in practice. So the next type is going to be dissociation. So dissociation, there's kind of arguments about whether this actually is a type of reaction or not. I consider it to be a reaction type, so we're going to learn about it. It's one that you've all seen before. Basically, for a dissociation reaction, you have some ionic compound that dissolves in water and it produces its ions. We saw this in Unit 3 when we were doing our big reactions lab, where you took some solids, dissolved them in water, and then tried to see if they conducted electricity using the conductivity meters. So anything that's ionic will break apart into its ions when dissolved in water and allow it to conduct electricity because you have free-flowing charge. and the products of the solid are different from the products of the reactant, or of the products of the solid are different from the products of the aqueous solution that gets produced here. So because the properties are different, I consider it to be a type of reaction. So the description for this one, you have an ionic compound. That dissolves in water. To form its ions. So for the general reaction format for this one, I'm going to use M to represent metal and NM to represent nonmetal, because we know that ionic compounds are formed from a cation and an anion. Generally, that's a metal and a nonmetal. Exceptions, of course, occur if you have ammonia, which is NH4 as our polyatomic ion. Then you would have just nonmetals exclusively. So here, if you have a metal and a nonmetal compound, MNM, this is a solid that when dissolves in water will break up to form ions. So the way we represent this is you have your arrow with H2O right on top of it like that. So this is telling you that water is not participating in the reaction, but it's necessary for this to happen. So when this thing dissolves in water, it's going to break up to its ions. So your metal will have a positive charge. Because it's dissolved in water, we give it the state of matter aqueous. And then you will have your nonmetal that forms its ion. Nonmetals always form anions, so we're going to put the negative charge right there. And again, because it's dissolved in water, this is aqueous. So this is your general reaction format. You can write in any example you want. So our reactants in this equation, it would be an anionic compound. It will be one singular ionic compound. Recall for this part, reactants, not water. Water is not a reactant. It's necessary for the reaction to occur, but it doesn't participate in the reaction. So if you're going to predict products for this one, you're dissolve the ionic compound into its ions. So remember, the definition of an ion is a charged atom or a charged group of atoms if they're polyatomic. So your ions must have charge. If you break that thing up without putting the charges on it, you're assuming it's a different type of reaction. You're assuming it's breaking down to form neutral atoms, which is not the case for dissociation. Has to be ions. So that brings us to the next type of reaction, which is decomposition. So in this case, you have one reactant that breaks down into multiple products. So your reactant here is one reactant. It can be of many different types, but what we are going to assume for our purposes is that the singular reactant will always break down to form the elements that make up the compound. This isn't always the case, but for our purposes, we're going to assume it's true. So let's say you have compound AB, and this thing undergoes some change that you can get it to chemically break that AB bond to form A plus B2. Let's say that B2 exists as a diatomic. So this could be a general reaction format. One reactant breaking down into multiple products. So how to predict products? We're going to assume that our singular element or our singular compound breaks down into its elements. So break compound into its elements. The important note here is to look for diatomics. So let me give you some other example that is not just with general reaction language. Let's say you had something like NaCl, sodium chloride. If this thing were to decompose and break down into its elements, it breaks down into Na and Cl, sodium and chlorine, but chlorine is a Hofbrinkel, it's a diatomic element. So that means in its elemental form, it exists as Cl2. So you would need to write it like this and then balance in order to fully predict the products correctly. So I'm gonna leave this example like this. I'm not gonna balance it. You can do that on your own and then find another example to include. Okay, now we get to the next page, the fun ones. So then this type of reaction, combustion, is a special type of reaction in which you have an organic fuel. So we're gonna write this in as the description. An organic fuel. When I say the word organic, I don't mean like you go to the store and you buy it like in the organic section and it's fancy and it costs more money. I mean, it's made up of carbons and oxygens and hydrogens. So organic is, let's write a note up here. This is a carbon-based fuel. So carbon-based fuel, organic fuel, reacts with oxygen. And this is oxygen in the air. And every single time you get the exact same products. You produce carbon dioxide and water vapor. So you have some organic fuel. It can be a solid, liquid, or gas. It reacts with gaseous oxygen in the air, and then you end up with gases as your products, carbon dioxide and water every single time. So there's two ways you can write the general reaction format for this one. You can have just straight hydrocarbons. You can have some CH compound. I'm going to put the subscripts X and Y to represent any subscript number. So carbon and hydrogen react with oxygen in the air and they produce carbon dioxide and water. That part doesn't change. But you could have an organic fuel that also contains oxygen. We've seen examples of this before. So you could have CXHYOZ, and this could be your organic-based fuel that reacts with oxygen in the air to produce carbon dioxide and water. So your reactants every time are some carbon-based compound. And elemental oxygen. Predicting products for this one is very easy because your products never change. Products are always carbon dioxide and water. And remember, these are in their gaseous form. The only thing that can change for these is if you end up, when you go to balance them, you may have to do that doubling trick, remember, because if you end up with a CHO fuel, you'll have oxygen in two places in the reactant side, which are harder to balance. So as a reminder, you might want to write yourself the reminder when balancing, you need to go CHO. All right, so write yourself an example in there, and then we're going to talk about single replacements. Single replacements are really fun. So for single replacement reactions, you have some singular element. And that single element reacts with a compound. If your single element is more reactive than the like element in the compound, the reaction will occur. So this doesn't mean that anytime you see some sort of reaction that you have a single element and you have a compound, it doesn't mean that it's a single replacement that will happen. You have to consult a certain set of rules called the activity series, which we will learn how to use tomorrow, to determine if your reaction is going to actually happen. So your reactants for this set, you have one element and an ionic compound. So there's two types of single replacement reactions, metallic and halogen. I put the two names for you right here. So in a metallic single replacement, your singular element is a metal. So I'm going to call that metal M1. So let's say that a metal wants to react with a compound M2X. Here in this reaction, your like elements are the metals. Your singular element is a metal, and then you have an ionic compound in which you have a metal bonded to some nonmetal. That nonmetal we're calling X. If this reaction is going to happen, metal 1, your singular metal, needs to be more reactive than the metal that's in the compound because this is the like metal. So if that is the case, M1 will come in and replace M2 in the compound, kicking M2 out to become the singular element. So M2 will get kicked out on its own, and M1 will form an ionic compound with X. Alternatively, if you have halogen single replacement, in this case, we're going to call your halogen X1. So remember, halogens are anything in group 7. So this would, your singular element here would have to be fluorine, chlorine, bromine, iodine, one of those options. So your singular element X1 wants to replace its like element in the ionic compound. So in this case, you have your metal bonded to some halogen, X2. If your halogen's more reactive, it'll kick X2 out to become, to be on its own, and it will replace X2 in the equation just like that. So remember, this is an ionic compound formula. Halogens are in group 7, which means they are non-metals, which means in an ionic compound formula, they have to come second, unlike metals, which have to come first in the compound formula. So that's why when I wrote these, I wrote M1X and MX1, because what's happening here is your metal has to go first, then your non-metal in an ionic compound formula. So how are we going to predict the products for these? First thing to note is your like elements will swap. And they'll swap positions only if your single element is more reactive. How do we decide if it's more reactive? We consult the activity series, also known as the reactivity series. If you look on the very, well, not the very front, the second page of your notes, you'll see I put some references in here for you. So this is the activity series. It's used to predict the outcome of single replacement reactions. We're going to learn how to use this tomorrow, but I want you to be aware that you have this in here for you. Okay, so then next type of reaction. Scroll all the way down there. All right, so next type of reaction is going to be double replacements. So description for these ones. In a double replacement reaction, you have two ionic compounds. These ionic compounds swap partners to produce two new ionic compounds.
What are you doing?
One of these ionic compounds must be a solid precipitate. If you don't get a solid precipitate at the end, then the reaction won't occur. So In order to figure out if a solid precipitate is going to occur, you have to consult another set of rules. It's the other reference that you saw in there, the solubility rules. We're going to, again, learn how to use those tomorrow. So our reactants for this situation would be 2 ionic compounds. So for the general reaction format, let's assume that you have some ionic compound A, B. This ionic compound reacts with compound C, D. These things are going to swap partners according to a rule I call the in-Z-out-Z rule. Your metal from one compound will bond with the non-metal from the other compound. So here, A represents a metal, D represents the non-metal from opposite compounds. These are your outsies. I'm calling them your outsies because they're on the outside of the reaction. B represents the non-metal from one compound, and C, the metal from the other compound. So these two things will want to bond. They are your INZs. So B and C will form a new compound, A and D will form a new compound if one of them is a solid. So you would have new compound A, D, plus compound C, C, B. Note here that I wrote C first and then B because, again, C is your metal, B is your non-metal. So one of these must be a solid. So you would represent that with the solid state of matter, S in parentheses. So to predict these products, you're going to use the in-Z-out-Z method. So in-Z, out-Z to swap partners. But it's not just as easy as like swapping the partners and calling it good. You have to first consult consult the solubility rules. If one precipitate and one aqueous, reaction occurs. We'll figure out more about what this means tomorrow. For right now, just trust me that this is true. So that means no precipitate equals no reaction. The last thing to know about these is because you're making ionic compounds, new ionic compounds, that means you have to crisscross. Because you're making new compounds, you want to make sure that the crisscross happens so you can get the new formulas for these ionic compounds. So you can write yourself an example in that box right there, and then we will learn how to actually predict products for all these 6 reactions tomorrow in class.